In the screencast, we are going to talk about hydrocarbons. Now, hydrocarbons are really the simplest of all organic compounds. They only contain carbon and hydrogen. Now, we can break these into kind of two categories, and one category is a saturated hydrocarbon. And when we talk about a saturated hydrocarbon, this is basically alkanes, right? But another way to look at it would be to say it's all carbon and hydrogen with no double bonds or triple bonds. So the way to kind of think about that is that it's saturated with hydrogens. Now, unsaturated hydrocarbons right, which we're going to look at later, are things like alkenes, which are double bonds, alkynes, which are triple bonds, and they're showed here in the image, and aromatics, and these all contain double or triple bonds. And they're all shown here. So this would be an example of a saturated hydrocarbon, and these would be unsaturated hydrocarbons. Now, most of our life processes are based on the reactions of functional groups. And since alkanes have no functional group, they aren't really abundant in the human body. However, compounds in human cells contain parts consisting solely of carbon and hydrogen that behave very much like hydrocarbons. And we'll look at that particularly when we get into lipids. So to understand the chemical properties of the more complex biomolecules, it's really useful to have some sort of understanding of the structure and physical properties and chemical behavior of hydrocarbons. And so that's why we're looking at them. So we are going to start by looking at alkanes. And we are going to look at common alkanes that are small. So alkanes can be represented with a general formula CnH2n plus 2. So these are going to have a general formula which is CnH2n plus 2. So, for example, if we look at methane, methane has one carbon, and let me do this by methane, right? Methane has one carbon, and so to predict the number of hydrogens, we take 2 times 1 plus 2, and that gives us CH4, okay? The carbon atom there is at the center, and so we can see a space-filling molecule here, but it would look like this if we looked at that expanded structure. Now, the carbon atom, when we look at its geometry, is it forms a tetrahedron, and so I want to remind you that this would have, that carbon would have a tetrahedral geometry. So the carbon has tetrahedral geometry, right? Now, methane is the primary compound in natural gas, and so tremendous quantities of natural gas are consumed worldwide because methane is really an efficient, clean burning fuel, and so it's used to heat homes, cook food, and power factories. So you may be familiar with methane gas. Now, the next alkane we're going to look at is ethane. And so if we come here, we say we've got 2 carbons in ethane, and so to figure out how many hydrogens, we would take 2 times 2 plus 2, and that would give us C2H6. This molecule can kind of be thought of as a methane molecule with one hydrogen removed and a CH3 put in its place. So it's going to look like this, where we're taking this hydrogen there, and I don't like that I chose gray, so let's do that in red. And basically we're replacing it with a CH3 group there. Now, again, the carbons here have a tetrahedral geometry. And I want to remind you, if something has a tetrahedral geometry, the angles here are, bond angles are 109.5 degrees. And so that's the bond angle for that tetrahedral geometry. Now, ethane's a minor component of natural gas. The third alkane we're going to look at is propane, and it's got 3 carbons, and we've got C3H2 times 3 plus 2, which gives us C3H8. And the way that that's shown is here. So we're going to make sure we can read all our hydrogens there and that all our bonds look good, right? So all the bonds are showing that connection between the carbon and the hydrogens. Now, again, basically what we did is we just added that CH3 on here to this part of the molecule. Propane is used extensively as an industrial fuel as well as for home heating and cooking. At the beginning of the chapter, I showed an example of a propane torch. And so this is the molecule that's used for the fuel for that. Now, the fourth member of the series is called butane. And we have 2 images of butane here. And butane has the molecular formula, which is C4 and then H2 times 4 plus 2. And so it'd be C4H10. Now, what we find here is that we can have 2 arrangements of these 4 carbons. We can have them all arranged in a line like this, which is called N-butane, and the N there stands for normal. So that would be normal butane. And that just means for us, a normal alkane is where everything is in a line. Then we can also have isobutane here, where we still have those 4 carbon atoms. So we've got 4 carbons here. We've got 10 hydrogens, but we can see that instead of being in a normal line, we have a CH3 group that branches off this interior carbon. Because of this, this particular molecule is called isobutane, but this would be an example of a branched alkane. And you can see here, this would be a normal alkane, and this would be a branched alkane. So one of the questions in your book says, classify the following alkanes as normal or branched. And I wanted to look at this because I want to show you something. When we're trying to decide if something is normal or branched, the carbons don't have to be in a straight line. They can twist around. And so when we look at this and kind of highlight through here, we're highlighting the longest continuous chain of carbon with no branches. So you want to highlight the longest continuous chain. And if there are no branches, then it's going to be normal. Now, if we look here and we try to highlight the continuous chain, and we can go from either direction. So for funsies, I'm going to start over here at the right. We could highlight down through there, and that's got 1, 2, 3, right? But that's not the longest chain. And so because I can come here and try this and go right like this, and now there's 1, 2, 3, 4. And so that's the longest continuous chain where it makes where each of these are connected to each other. Now, what that means here then is that CH3 is what we call a substituent. It's not part of the longest chain, it's branched. And so this then would be a branched an example of a branched hydrocarbon. So we have an example here of a normal hydrocarbon, and then we have an example of a branched hydrocarbon. Now, I mentioned here that these can twist around, and the reason that these can twist around is because there's rotation around the carbon-carbon bonds. And when there's rotation around the carbon-carbon bonds, these are called different conformers, and they can have different conformations. So conformations are just the different arrangements of atoms in space, and these are achieved by the rotation around single bonds. All right. Now, different conformations do not represent different structural isomers. So remember, structural isomers have the same chemical formula but are arranged in different orders, right? Well, these, if you look at butane, for example, butane, and this is normal butane, is CH3, CH2, CH2, CH3. This is also CH3, CH2, CH2, CH3. These would be considered different conformers because they have that same structure. So they're structurally the same, but this, what we're doing is we're just twisting this molecule or turning it or rotating it. And you can see the rotation shown here. So basically what we're doing is if we're looking down, right, this bond right here, basically what we've done is it's the same as saying we're looking at this bond, and we have just taken and rotated this up, and these two hydrogens have rotated down. And that's what it's showing you here, is that there's a rotation there. Now, we recognize that the representation then of these two is different, and so we call these conformers. Okay, and that would describe the rotation between them. Now, when we talk about structural isomers, for example, the N-butane and the isobutane are examples of structural isomers because their connectivities there are different. But in this case, with these conformers, the four carbons are bonded in a continuous chain. And so since that order of bonding is not changed, those conformations these are really the same molecule. They're just shown differently. So I want us to do an example. Now, the first thing that you do when you're going to compare these two is you need to make sure they have the same chemical formula. If they don't have the same formula, they're different molecules, they're not going to be isomers. So when we look, for example, at this molecule here, we see that there are 5 carbons, and then we count our hydrogens. There's 3, 6, 9, 10, 11, 12. And so we've got H12 here. And then when we come over here and look, there's 1, 2, 3, 4, 5 carbons. And so there's 5 carbons, and we count our hydrogens, and it's H12. So these can either be the same molecule or they can be structural isomers. So then the next thing we need to do is we need to highlight the longest chain. And so when we go through and do that, that's our longest chain there. And then here would be our longest chain here. And both of those longest chains are 4 carbons. Now, I want you to notice this has a CH3 off the second carbon, and this has a CH3 off the second carbon. And so these would be an example of identical molecules. So these would be identical. Okay, now we're going to come down here and we're going to do the same thing. We've got 1, 2, 3, 4, 5. So these would be C5H12, and here would also be C5H12. And when we highlight these, oops, that's not the highlight, so hold on just a second. When we come over here to our highlight tool, when we highlight these longest chains, we can see that they are 5 here. So these two here are identical. But if we compared this to this, those two here, this one and that one, would be structural isomers. Because the longest chain here is 5, but the longest chain here is 4, and there's a CH3 group that's off the 2. Well, here, off the second carbon, there's no CH3 group. So they have the same chemical formula, but they're arranged differently with different connectivity. So those would then be structural isomers. These are just conformers of each other because we're showing there's a little bit different rotation. All right, so that ends our screencast on hydrocarbons and different conformations. In the next screencast, we'll look at how to name different alkanes.